Hello, everyone. Great. My name is Byki Huntjens, and I am the program director of the undergraduate optometry course at City University in London. And I'm going to talk, as Joan just said, about the complexity of the spatial profiles. Before I start, though, I do want to thank Irene Torrey, who is here in the audience today as well, for all her hard work in obtaining all the data that we are presenting during this conference. I also would like to thank John for allowing us to use the map test for all the studies that we did, and Chris Hammond and Omar Maru for giving us access to the Twins UK data. So, as we all know, macular pigment typically peaks at the center of the fovea, and then following typically an exponential decline away from it. But the literature has also reported deviations from this exponential profile. For example, secondary peaks. And these secondary peaks, they tend to occur between 0.5 and 1.2 degrees away from the fovea. And not only have these been found using the subjective psychophysical method, using heterochromatic flicker photometry, but we can also see these using the objective fundus autofluorescence. So it has become apparent that macular pigment may show this ring when we look at these FAV images, but there have also been reports of a central dip. However, we need to take into account that when we are looking at these FAV images, very often the literature, when they start classifying these macular pigment spatial profiles, it's really purely based on the visual deviation from an expected exponential curve. And another problem that has been highlighted is that these deviations, the amplitude of the deviations, are generally quite small. So we were wondering really if they are statistically reliable. And so there have also been studies to look at if this secondary peak or this ring-like structure is an actual, a real perturbation, or is it just an artifact of the instruments that we are using. So last year, our group reported ethnic differences in the spatial profiles when we're taking the 3 variations into account. And we used instrument based on HFP. And really what we were trying to do is to get some sort of objective classification system for this, while we're going to use the coefficient of repeatability of the instrument at all the different eccentricities that we were measuring. So I would like to explore this a little bit further. So today I would like to summarize the options that we have to report the spatial density distribution of macular pigment, and preferably come to some sort of agreement, and hopefully actually during this conference, where we can come to an agreement on how to report this in our future studies. And I really would like to do that because at the moment there doesn't seem to be any consensus at all as to how we report our macular pigment spatial profiles or the distribution of it. And really I think it's very important if we want to have a look at change of macular pigment over time, but actually more importantly if we start comparing our results between the studies. And it shouldn't really matter which macular pigment technique that we're using. We should really try to come up maybe with some sort of, unified consensus as to how to report this in the future. So to do this, we have used 2 different instruments and throughout, and just as a comparison. So this is not limited, obviously. We can do this also for any of the instruments that you use in your own practice. So we included 40 subjects that were either seen on 2 separate visits when measured by the HFP, or they received 2 FAV scans. We made 2 FAV scans, and the FAV was based on the 2 wavelength fundus autofluorescence during 1 visit. And the macular pigment that is represented by our macular assessment profile test based on HFP the macular pigment is an average of 8 measurements at each eccentricity, and we included 7 of those, of which 5 are central. And when we look at the fundus autofluorescence, the macular pigment is represented by an average of 8 radial scans. And obviously you can use any eccentricity, but we wanted to include eccentricities that were very similar to the HFP, so we could compare our objective profiling system. And just a small point here, we just wanted to show that the mean standard error of all of these macular pigment readings at all these eccentricities was identical between the 2 instruments. So let's have a look at the different ways in which we can report macular pigment. So I start off by looking at the single measurements, and it's a very traditional way of reporting macular pigment. And I think we all use it, or have used it at least in the past. And it's a great way of showing how this would reflect then when we use spatial profiling. So I do want to point out, though, that when I'm talking about a single measurement of macular pigment at a certain eccentricity, I am not talking about the average of the macular pigment within a radius up to that eccentricity. And I'm only saying that because some of the instruments, the output of that will actually offer you that number. So what we're talking about today is the measurements of macular pigment at a certain eccentricity. Now here are the results of our repeatability study, and I wanted to show you here on the top are the results using HFP for all the central 5 eccentricities, and at the bottom here we can see the results for FAV. Now I would like to draw your attention to this column here, the coefficient of repeatability column. The coefficient of repeatability was calculated as 1.96 times the standard deviation of the differences between the 2 scans. And really what you can see with HFP, we found using our map test, is that the coefficient of repeatability is very similar at all the eccentricities. However, when we look at FAV, we found that at 0, it was quite unacceptable that it was this high, the core. So what we decided to do is to actually ignore those points and start looking for the next eccentricity that could be replaced for central measurements of macular pigment. And what we decided to do is to include the 0.1, where the core is still quite a little bit high, but we felt it was acceptable to use that further on. Now I do show here also the core for 0.2 and 0.5, and that's as a comparison really, but what I want to point out is that we didn't use or include this data in the further analysis when we look at spatial profile. So for HFP, we use these eccentricities, and for FAV, we use the same eccentricity, but instead of 0, we're using 0.1 degrees. So now we've got our individual macular pigment measurements at all these eccentricities, so we can start profiling. And we have proposed this objective classification system, as I mentioned before. And how we've done it is that we plotted the individual macular pigment at all the different eccentricities. Then we fitted an exponential curve through it. And then just to make it visible for yourself, I plotted also one core above and below for each of these eccentricities. And we did that for HFP, and we did it obviously for FAV. And then what we did is when the macular pigment was more than one core away from the exponential fit, we would then classify this as a ring-like profile or a secondary peak. And if the macular pigment at 0 for HFP or 0.1 for FAV was deviated more than one core away or below the exponential profile, then we decided that that would be called a central dip. So let's have a look at the repeatability of this objective spatial profile method. And what I would like to point out is that the strength of the agreement between objectively classifying the first scan versus the second scan is visualized using the overall percentage agreement and the kappa value, sorry for that, together. So when we have a look at HFP and FAV, we find that actually that this objective profiling system is highly repeatable. Now, a little bit more detail on the HFP results. There was one subject who had a central dip on the first scan, the first visit, and that changed to an exponential on the second visit, so it was a different scan. And there was also one person who had a ring-like profile on the first visit, and that changed to an exponential profile. And then if we have a look at FAF, there were 3 subjects out of the 40 that changed from an exponential profile or a ring-like profile. Sorry, they changed from a ring-like profile to an exponential on the second scan. So from this, we concluded that actually this objective profiling system is highly repeatable. And we also concluded that actually we can now show that deviations from the exponential profile are not due to measurement error, but they are actually real perturbations. And this is in agreement with a study that has already been published in 2009 by Kirby and co-workers, who found the same thing when he included the macular densitometer based on customized HFP. Now, we've seen in the literature that visual inspection of FAF images is a very common way to classify. And we wanted to see how repeatable that actually is. So we asked an experienced observer to look at both the FAF scans that were available for our 40 subjects. And that was in random order, and he was blind to his previous results. And what we find that, although that the agreement was statistically significant, the kappa value did show that it was only a moderate agreement. So if we compare that really to our objective classification system, we felt that that is more reliable than what we currently use when we visually look at FAF images. When we include all the 80 FAF images, so that's 2 per person, and we compared all the results from our experienced observer to the results that we had when we're doing objectively, then we find that the agreement is rather poor. And actually, I think this really highlights the fact that it's so difficult to start comparing the classifications that are used in all our studies when you're doing it in your own in the visual way. Not only the way how to look at it and classify it, but on top of that, really we're also about the definitions that we use. So this problem becomes even more apparent when we started to reanalyze 314 FAF images using our objective spatial profiling. And then we compared that, and this was a study that was published in 2014 by Tarek and colleagues. We compared our objective spatial profiling to an experienced observer looking at all the images again, using the same classification or the same definitions for exponential, ring-like, and central dip. And what we found is actually that we lost a lot of central dips when we did it in the objective way. And really from that we concluded that visually it seems that we tend to overestimate these non-exponential profiles. It's even worse when we have a look at our objective spatial profiling and then we compare that to the original data. Now, obviously, there is again a problem because this is again based on visual assessment. So we're almost losing about 50 people when we compare it to our objective spatial profiling. And that's not only because of the visual problem, it's also based on the fact that the definition was slightly different between plateau and central dip. But on top of that, when we had a look at the objective on the FAF images, we used the find foveal function, and the original paper didn't do that. They located the center of their macular pigment as the peak macular pigment. So there are quite a few differences between the studies and the results that are reflected like that. So really, in absence of a clear absolute foveal marker on the fundus autofluorescent images, we are seeing quite a lot of possibly scan misalignment. And that makes classification objectively quite difficult for FAF if you compare it to HIP. So as an alternative, we thought maybe what we could do is actually calculate as kind of like an integrated macular pigment, and we can start using that. So at least we can compare that between all the different instruments. So we've got 2 different ones. We have an average and an integrated. And if we look at the average, we published this paper in 2014 where we're having a look at the MPOD-F, and I just quickly want to show you how that was calculated. The individual macular pigment measurements at each eccentricity is used to calculate the transmittance at those corresponding eccentricities. Then the average of the blue light transmittance, TF, which is a three-dimensional area-weighted representation of the transmittance over a certain area, is then calculated by calculating the volume of the transmittance over an aperture, assuming that this is 360 degrees around or the same, and by dividing that to the area of the aperture. And then what you get is an average transmittance, which you can then convert back to macular pigment average by taking the inverse log. And first of all, I would like to point out that the MPOD-F decreases as the area increases. Obviously, this happens because when the area increases, the transmittance over that area increases, and because of the inverse log, we're seeing a decrease in MPOD-F. I would like to point out that despite the fact that we had quite a high core at 0.1 using FAF, this is actually not really reflected anymore by the time you increase your area. So the core was really good for FAF as well. Alternatively, we can also measure the integrated macular pigment, and this is based on the trapezium rule. And it's really a 2D or a rectangular coordinate system where we're adding the average macular pigment over the area. So as you can imagine, as the area increases, the macular pigment integrated also increases. And the cores were quite similar between the instruments. I do have to point out that the percentage of variance was quite high for HFP, but it's because we have quite a high standard deviation within the group, so it's really sample specific. Now let's have a look at those individual parameters and how those reflect the spatial profile, especially because spatial profiling is, as I mentioned before, maybe not the way forward if we're looking at these FAF images. So what we've done is we included 226 patients, and they're all healthy and young, and we used HFP, and because we used HFP, we felt it was appropriate to do the spatial profiling the way that we did it before, so this is the objective spatial profiling. And what we found is that the people that showed an exponential profile have significantly less macular pigment. It doesn't matter if it's at 0 over an area, so the MPOD-F, or even the MPOD-Int. And really, it confirms the fact that when we're looking at patients who have a non-exponential profile, these people have significantly higher macular pigment, up to 2 degrees or even up to 4 degrees. So in conclusion, regarding the spatial profiling, we could say that objective spatial profiling is more reliable than visual, and that's probably not a surprise. I do think that we have to start including the core, definitely up to 1.2 degrees, if we really want to make a conclusion as to if this patient has got an exponential profile or a non-exponential profile. And so the mean standard error is really not enough to show this. The problem, though, is that it seems that FAF actually doesn't really pick up the central dips. And we believe it's due to the scan misalignment and the fact that we haven't got this absolute foveal marker to make sure that we are taking the macular pigment exactly at 0. So in absence of this classification system that now we can't possibly use for all the different techniques that we use to measure macular pigment, we wanted to propose that we start reporting on the integrated macular pigment. And it's not something that I want you to replace your current classification system with. That's not at all the case. But what I do want to propose is that we start using either up to 4 degrees if you want to go for total, or central up to 2 degrees. And you can choose, obviously, if you want to do integrated on an area weighted or, an average of an area weighted or integrated. But really, if we start reporting these results, we can actually start comparing between our studies. And I really think that is the future. So I just want to show you also some soon to be published exciting data that we found when we had a look at HFP, the spatial profiles. And although in the past we have reported significant differences in spatial profiles between these two ethnicities, we are very happy to now also have got a third ethnicity. And what we found is that because we used HFP, we still thought it was appropriate to use the spatial profiles. And what we really found is that in the South Asians, there was significantly more prevalence of ring-like structures, while in the blacks, it was more common to see a central dip. And this was not really related to any like gender or age, any of the covariates that are related with AMD. We also had a look at the spectralis, and I'm not going to go into this too much detail because Irene is here with a poster, so please go and see her later today. But we looked at the inner retinal thickness, and we compared it versus macular pigment. What we really were trying to do is to see if foveal architecture is in any way related to these spatial profiles, and if we can explain them by looking at the anatomy. And so we looked at the foveal width, we looked at the slope. And as I said before, Irene has got a poster later today, but I just wanted to point out that one of the findings is that even though ethnicities, within the ethnicities, we see a lot of significant variation in macular pigment. Within the ethnicities, we also see a lot of variation in foveal architecture. But actually, we found that the foveal architecture cannot explain these differences in spatial profiles. And it's quite nicely visible in this graph, where here at the bottom we can see the macular pigment optical density per ethnicity for the 3 different spatial profiles, which significantly changed or differed. But if we look at the inner retinal layers, for example, they are all identical for the 3 different profiles. So in summary, it's still orange, so I can still go for a bit. In summary, I wanted to say that ethnicity is an important part in variations that we see in macular pigment, and especially the spatial profiles. And so I wanted to point out that non-whites, in general, you can find more non-exponential profiles. But while accounting for the ethnic variations in retinal anatomy, we can't really explain that by the foveal architecture. And the last point I really wanted to make is that, and I said it already before, but I really hope that we can come to some sort of consensus where we start to look at unifying our results so we can start comparing between studies, no matter which instrument that you use. Thank you very much.
We're open for questions now.
Have I preached too much?
Can I just ask,
Yeah.
when you did the ethnicity comparison, were they all from the same location, or those different locations globally?
Yes, so we've used the same eccentricities, the same methodologies that we explained.
Global location.
Oh, yes. No, these were all London-based, so in the UK. Yeah. And we do have actually data on if they were born in the UK or when they were coming, but I don't think there was much variation, actually. I think maybe also the numbers were quite small. Sorry, yeah.
They were all London-based, and the spread of people who'd lived abroad was quite similar across the three groups.
Oh, hi, Todd.
And the FAV images, you said they were not foveally centered. That was a problem. How do you find the fovea?
Yeah, so the original paper by Tarek, what they've done is they looked at the almost like the maximum reflectance, but manually. So they went into the center of the reflectance, the highest reflectance, and then manually looked for the peak. And actually, when we talked to the authors, they were thinking as well that maybe that was a problem because then you could potentially miss some of these non-exponential profiles. So we discussed it for quite a long time because how else are you going to do it? But there is this function within the FAF which you can use. It's called find fovea. So it will put it in the center. And then what we done is we went to the radial scans, so the 8 radial scans. And if the find fovea function would put the center somewhere on a blood vessel, we had to do it manually anyway. And then we would look through the radial scans where the variance was least. So that was the difference in, but you still don't know if you're actually in the center. So I'm still considering that is probably our main problem, that we can't find these central dips.
But did you also compare it with OCT?
No, this was 2 wavelength fundus ultrafluorescent not attached to the OCT, so no. And I'm wondering actually if that would help a bit. Well, if we would have this wonderful machine, I still have my eye on, John. If you can take both images at the same time, then obviously that would be the best. So I'm very keen on having a look at those profiles.
We're going to have to move this on to toss, and I'm going to ask that you hold questions. I know Paul has one too, but otherwise we're going to run late in the session. So please bring your questions forward and grab our speaker a little bit later.
Yes.
Thank you.
Thank you.